Billions of years ago, Mars was a planet that bore little resemblance to the arid, dusty landscape we see today. Imagine a world with blue skies, flowing rivers, and vast oceans. This is the Mars that scientists believe existed long before it transformed into the barren, rocky desert that has captivated human imagination for centuries. But how did Mars change so dramatically? What processes reshaped this planet from a potentially habitable world into the inhospitable place we now see through the eyes of rovers and orbiters? To understand the fascinating transformation of Mars, we must delve deeper into its history and the evidence uncovered by modern space exploration. One of the most compelling pieces of evidence for Mars' wet past comes from the data collected by NASA's rovers and orbiters. These robotic explorers have provided us with a wealth of information that paints a picture of a very different Mars. The surface of the planet is dotted with features that strongly suggest the presence of liquid water in the distant past. River valleys, lake beds, and the presence of minerals that only form in water are all indicators that Mars was once a much wetter place. One of the most striking features on Mars is the Valles Marineris, a colossal canyon system that dwarfs the Grand Canyon on Earth. Stretching for over 4,000 kilometers, about 2,500 miles, and reaching depths of up to 10 kilometers, over 6 miles, the Valles Marineris is a testament to the powerful forces that once shaped the Martian surface. Scientists believe that this immense canyon, along with other channels on Mars, was carved out by flowing water, possibly fed by ancient rivers and lakes that once crisscrossed the planet. The idea that Mars once had vast bodies of water is further supported by studies of the planet's northern lowlands. These low-lying regions appear to have been an ancient ocean bed, possibly holding a body of water larger than the Arctic Ocean on Earth. Estimates suggest that Mars' oceans could have covered about 19% of the planet's surface, roughly equivalent to the area of the Atlantic Ocean. This ancient Martian ocean, combined with evidence of lakes and rivers, paints a picture of a planet that could have supported life. The climate of early Mars would have been far more conducive to life than the cold, dry conditions we see today. Picture a planet where lakes dotted the landscape, rivers wound through valleys, and rain might have occasionally fallen from the sky, feeding these waterways. The discovery of hydrated minerals, such as clays and sulfates, on Mars supports this vision. These minerals only form in the presence of water, indicating that Mars once had a wetter and potentially warmer environment. Sedimentary structures found in ancient lake beds also suggest that Mars had a dynamic water cycle, similar to that of early Earth. These lakes could have been havens for life, much like Earth's primordial soup, where simple organisms first began to emerge. If Mars had water for long enough, it's conceivable that microbial life could have developed, thriving in the nutrient-rich waters that once covered the planet. But if Mars was once a wet, potentially habitable world, how did it transform into the cold, desolate planet we see today? To answer this question, we need to explore the planet's magnetosphere and atmosphere, two critical components that protect and sustain life on Earth but are now absent on Mars. A planet's magnetosphere is a protective shield generated by the motion of molten metal within its core. This magnetic field plays a crucial role in maintaining a planet's atmosphere by deflecting harmful solar radiation and preventing the atmosphere from being stripped away by the solar wind. A stream of charged particles emitted by the Sun. Earth, for example, has a strong magnetic field that extends far into space, protecting our atmosphere and making life possible. Mars, too, once had a magnetosphere. However, being smaller than Earth, Mars cooled more rapidly. Scientists believe that as Mars' core cooled and solidified, it lost its ability to generate a magnetic field. This likely happened about 4.2 billion years ago, leaving Mars vulnerable to the relentless solar wind. Without a magnetosphere, Mars' atmosphere was gradually stripped away in a process known as atmospheric sputtering. Over millions of years, this process reduced Mars' once thick atmosphere to the thin shell we see today, less than 1% the density of Earth's atmosphere. As Mars lost its atmosphere, it could no longer retain heat, leading to a significant drop in temperature across the planet. The average surface temperature on Mars today is around -80 degrees Fahrenheit, -62 degrees Celsius, far too cold for liquid water to exist on the surface for any extended period. Without a thick atmosphere to trap heat, any remaining water on Mars either froze or sublimated, turning directly from ice to vapor and escaping into space. The loss of water, combined with the disappearance of the atmosphere, transformed Mars from a warm, wet world to the cold, dry planet we see today. The Martian surface is now dominated by vast deserts of red dust, with only the occasional polar ice cap hinting at the planet's watery past. Given the evidence of ancient water on Mars, the question arises, could Mars have supported life? Scientists believe it's possible. The presence of liquid water is a key ingredient for life as we know it, and if Mars had water for long enough, it's conceivable that life could have emerged. Early Mars had conditions similar to early Earth, where life first arose. Both planets had volcanic activity, a thick atmosphere, and liquid water, all essential ingredients for life. If life did exist on Mars, it would likely have been simple, single-celled organisms similar to the early microorganisms that thrived on Earth. These microorganisms could have lived in the nutrient-rich waters of Mars, possibly around hydrothermal vents, which provide heat and minerals that can sustain life. Hydrothermal vents are considered prime locations for the origins of life on Earth, and they could have played a similar role on Mars. Today, NASA's Perseverance rover is searching for signs of ancient life on Mars. Perseverance is exploring Jezero crater, which once held a lake. By studying the rocks and soil in this region, scientists hope to find biosignatures, chemical or physical signs of past life. Jezero crater was chosen for its delta deposits, which are excellent at preserving organic molecules and potential fossils. Perseverance is also collecting samples that will be brought back to Earth in future missions. These samples could contain clues about Mars' past climate and habitability, and potentially even fossils of ancient microorganisms. The rover is equipped with sophisticated instruments to analyze the chemical composition of rocks and soil, searching for complex organic molecules that could indicate past life. Why is it so important to study Mars' watery past? The exploration of Mars' history offers valuable insights into the history of our solar system and the conditions that lead to habitability. By understanding how Mars transformed from a wet world to a dry desert, we can learn more about the processes that shape planets and the potential for life elsewhere in the universe. Mars and Earth share many similarities, including polar ice caps, similar landforms, and a history of volcanic activity. By studying Mars, we can gain a better understanding of Earth's own history and how our planet has evolved over time. For example, Mars' volcanic regions, such as Olympus Mons, the largest volcano in the solar system, could offer insights into volcanic processes that also occurred on early Earth. The knowledge we gain from studying Mars is also crucial for future human exploration. Scientists and engineers are currently working on plans to send humans to Mars, and understanding the planet's history and resources is essential for these missions. Future explorers could use local resources, such as extracting water from ice or using Martian soil for growing food, to support long-term missions. This knowledge is vital for creating a sustainable human presence on Mars. The search for life on Mars is far from over. Future missions by international space agencies and private companies aim to dig deeper into the Martian surface and explore new regions. For example, the European Space Agency's ExoMars rover, set to launch in 2028, will drill into the Martian subsurface to search for signs of life, where microorganisms could be protected from harsh surface conditions. Advances in technology are crucial for these explorations. Innovations in robotics, artificial intelligence, and remote sensing are enhancing our ability to study Mars in unprecedented detail. These technologies allow us to analyze vast amounts of data and make discoveries that were previously impossible. I hope you found this journey through the history and future of Mars as fascinating as we did. If you enjoyed this exploration and want to stay updated on the latest discoveries from Mars, don't forget to hit the subscribe button and give us a like. Your support helps us continue to bring you amazing content on the wonders of the universe.